Hi, in this video, we will learn how to perform the Laplace transform by using the definition. This is the table that we use to perform the Laplace transform and the inverse Laplace transform. To master the knowledge of Laplace transform better, we can rearrange the table with the corresponding concept. In this video, we will show you how to use the basic Laplace transform definition to find the Laplace transform for a constant function, exponential function, and polynomial function. This is the definition for Laplace transform, where you convert the time domain signal into the s domain by using the integration from 0 to infinity. And your s domain, s is equal to sigma plus I omega. In exercise 1a, so let's find the Laplace transform for a constant function. So to perform the Laplace transform for 1 by using the definition, you can just substitute the ft inside this formula. Integrate the exponential negative xt, then you get exponential negative xt divided by negative x. So with that, you obtain this answer. And the limit can be presented in several forms, and these forms are acceptable in this study. Then we substitute the x equal to sigma plus I omega inside, and expand the exponential term. Next, we substitute the limit infinity inside, you get this, and limit 0 inside, you get this part. So for the exponential 0, you should be able to get 1. Refer to the exponential negative sigma infinity. So if your sigma is equal to negative, so in this case, you have exponential positive infinity. So you will get undefined result. It means if the sigma is equal to negative, your fx will return the answer to be not a number or NaN. So it means that your Laplace transform has no solution in this case, which is diverge. On the other hand, if your sigma is positive, then your exponential negative infinity will be equal to 0. So this part can be equal to 0. So this part is equal to plus 1 over x. So you get the result to be 1 over x for the fx. So in this case, you found that if the sigma is equal to positive, then you get a converged solution, where the Laplace transform result is well defined. As you can see, depending on the sigma, so there is a region of convergence. So in some region for the sigma, you get diverged solution. In some region for the sigma, you will get converged solution. So we want converged solution. For example, for the ft equal to 1, okay, when we convert to s domain, we get fx equal to 1 over x. This is only valid when x is greater than 0, or in specific, the real part for the x, which is equal to sigma, is greater than 0. So this is our region of convergence. And you should know that the fx equal to 1 over x is not valid at the region of convergence, where you might get infinity or not a number in this region, where your x is less than or equal to 0. In specific, the real part for the s, which is the sigma, is less or equal to 0. We can use this rule of thumb to find the region of convergence. So, depending on your pole, the region of convergence, which is the real part for the x, must be always greater than the pole. So if you have more than one pole, so you choose the maximum one, and then the region of convergence must have the real part of x greater than this. So in this case, you have the x equal to 0. So this is your pole, because it makes the denominator to be 0. At the bottom, you get 0 here for your fx. Therefore, we can say that x equal to 0 is the pole. With that, we can substitute the x equal to 0, which is the pole, into the rule of thumb, and we get the region of convergence. The real part of x must be greater than 0. So it gives the same answer like the previous one. This is for your extra information. The pole, which is s equal to 0, consists the important characteristic of the signal. So based on this pole, we can tell the ft equal to 1 as the 0 frequency and 0 decay rate. In this exercise, find the Laplace transform for the ft equal to c. Substitute the ft inside the definition. Integrate it, you should get this answer. Substitute the infinity limit inside, you get this term. Substitute the 0 inside, you get exponential to be 1 here. And then negative, you get positive here. And at the region of convergence, this part will be equal to 0. So your exponential negative x infinity will be equal to 0. So this can be cancelled, so you get c over x to be the answer. So in this example, you successfully use the definition to convert the ft into the fx. So in concept 1, okay, you must know if you have a constant function, let's say you have 5 here, so this is your ft. So when you convert to fx, you will get 5 over x. And if your constant is 6, then this is 6 as well. And if you want to convert back, refer to the below denominator, so you should get back your ft equal to 6. So bend your mind now for constant, this is the pattern. In this example, we will perform the Laplace transform on the exponential function, so you have exponential 5t here. Substitute the ft into the definition and then integrate, you get exponential negative s minus 5 here, so divided by the constant for the negative x minus 5. Then substitute the limit infinity and 0, you should be able to get this. By consider the region of convergence, your left part should be equal to 0, and on your right side here, so this term should be equal to 1. So with that, you obtain 1 over s minus 5. In more specific, this formula is only valid at the region of convergence. So this is the region of convergence. How can we know is 5? So we can use the rule of thumb. So we check the pole here. So the pole is equal to 5. So this is the answer. So with that rule of thumb, the real part for the x must be greater than the pole, which is 5. So you should aware that for your formula fx equal to 1 over x minus 5 here is invalid at this region. When you substitute it inside, you should get undefined solution. This is some extra information. So from the pole x equal to 5, you can tell the characteristic of the function. So x is equal to sigma plus I omega. When you compare, the omega is 0 and your sigma is 5. So in this case, you get the sigma equal to 5, omega equal to 0, which is true when you compare to the original signal ft, where you get the sigma is 5 here, where you don't have omega. In previous example, we take the Laplace transform for the exponential 5t by using this definition and you get this result, fx equal to 1 over x minus 5. And from here you obtain the pole to be 5. So with that, we can plot a graph where your real part is sigma and your imaginary part will be omega based on this definition. So since your sigma is equal to 5, you can draw this, and pole is indicated by the cross. So you see your region of convergence is greater than 5. So over this side, you can say your fx is valid here. And over this side, okay, is the region of your divergence. If we change the rate to be negative 6, so after perform the definition, you get 1 over s plus 6. So based on this, you get the pole to be x equal to negative 6, where you can see your pole is located here at the negative side, and this is the region of convergence, which means your fs result is only valid in this region only. In this example, let's have the exponential at, where a is the constant. So after perform the definition, you get the Laplace transform result to be 1 over x minus a. So bear in your mind, the most important thing is when you have exponential 5t, so your Laplace transform for exponential 5t, you should get the result to be 1 over x minus 5. So we see if this is positive, this will be negative. So if you change the rate to be negative, so in Laplace transform, it gives you 1 positive. So if you have Laplace transform result fx, okay, equal to this, and if you perform the inversion for the Laplace transform result, okay, so you perform Laplace transform inversion for this case, okay, based on the denominator, you should recognize this is exponential form, okay. So, and you have positive 5 here, you should get negative 5 here. So if this is negative, then you should get positive here. So you have to remember this pattern, it will be very useful for you. If you have constant equal to 0 here, so you'll just have 1 over x, you have the exponential 0t, which is equal to 1. In this example, let's find the Laplace transform for the polynomial function. So in this case, we have ft equal to t. Substitute the t inside the definition, then you found there are two different functions here. With that, we need to use the integration by part. We let the u to be t here, and then we let the dv equal to this part. And we differentiate du, you get dt. Then integrate dv here, you get v equal to this part. So for the integration by part, you have uv minus v du. So substitute all the uv and v du inside, you get this. So for this part, substitute infinity inside, you get exponential negative infinity. So this is 0. Substitute 0 inside t here, 0 multiply everything, you get 0 as well. Then for this part, you integrate, you get exponential negative xt divided by negative x here. Then you substitute the limit, so substitute infinity, you get exponential negative infinity, which is 0. Then you get negative negative positive, so 1 over x squared. So this is the final answer. So this is polynomial function also. So we perform the Laplace transform for the t squared. So you see there are two functions, therefore you use the integration by part. Let u to be t squared, this one, dv to be the rest. And then you perform the du, okay, you get 2t dt here. And for this part, you integrate, you get this. And substitute it into the uv minus v du formula. Then you have this. Substitute the limit inside, you get 0 for this term. And then for this term, you need to integrate. Luckily, from the previous example, we already get the answer for this integration, so we can just substitute. So you have 2 over x multiplied with this, which is 1 over x squared. So with that, you obtain the final answer to be 2 over x power 3. How about if we have t power 3? So let's take the Laplace transform. So in this case, you have t power 3 to be the u, and this part to be your dv. Then you get the du and v corresponding. And this is the uv minus v du formula. You just substitute inside. Then from here, you found that after you substitute the limit, you get 0. And then for this part, okay, you need to integrate. So we take out the constant, you have to integrate this part. So luckily from the previous example, you get this answer to be 2 over x multiply 1 over x squared, so you can substitute. So after you substitute, you get this, and the final answer is 6 over x power 4. How if your ft is equal to t power of n, where n is the order? Okay, so previously, if let's say this is 1, you get the Laplace result to be 1 over x. If this is t, you get 1 over x squared. If this is t squared, you get 2 over x power 3. t power of 3, you get 6 over x power 4. So referring to this pattern, we can see when the n is equal to 3, so you have 3 factorial, which is 6x power 3 plus 1. So when your n is equal to 2, you have 2 factorial divided by x power 2 plus 1. So if you continue, you're able to obtain this. So with that, we can say that for t power of n, then you should get n factorial divided by Sn plus 1. So this is the concept tree. We can also prove the concept tree by using this method. So in this case, your ft equal to t power of n. So we directly substitute inside the definition for Laplace transform and then perform the integration by part. Substitute the uv and v du into the formula. Then you can obtain this. Substitute the limit, you obtain the 0 on this part. And then on the right hand side, extract the constant, and then we are going to integrate this part. So when you look at the format, is the format same with the Laplace transform for t power of n minus 1, where this is your function ft. So same pattern, you can see that if you perform Laplace transform t power of n, this will be your ft. So with that, we can substitute this inside the equation and Laplace transform t power of n inside here. With that, we can obtain this equation. So when the n is equal to 1, 1 minus 1, you get t power of 0. So you know Laplace transform t power of 0 is 1 over s. So these two multiply together, you get x power of 2. And then when n equal to 2 here, so you have your n equal to 2, substitute. So 2 minus 1, you get 1. With that, Laplace transform t, you get 1 over x squared. You can substitute inside here. So multiply, you get the answer. And then if you continue, you will find the pattern, and this pattern help you to form Laplace transform t power of n equal to n factorial divided by Sn plus 1. The most important thing that you should know in concept 3 is, if you have a Laplace transform result fx equal to something with denominator x power 4, for example, let's say at the top is 1. So in this case, if you perform the inversion, so inversion of this, so you should aware that if you have x power 4, you should get the polynomial function t power of n. And to know what is the n here, so refer to the format n plus 1 will be equal to 4. So with that, you know the n is equal to 3. So when you substitute 3 inside, so based on this formula, t power of 3 will be 3 factorial divided by s power of 4. So at the bottom is correct, but at the top it will be 3 factorial. So what you need to do is, okay, divide the 3 factorial so that you get back 1 over x power 4 here. So at the same time, on the right hand side, you need to divide by 3 factorial also. So this answer is the answer for inverse Laplace transform for 1 over x power 4.